Okay, welcome everyone to the 126th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Christoph Winges from the University of Regensburg, and he will be talking to us about some remarks on the gay theory of exact infinity categories.
Thank you very much. Thanks for the invitation. So the plan for today is that I want to present to you a few statements concerning exact infinity categories and their K-theory, which have me helped a bit to understand the role that exact infinity categories play in this story and how they relate to the K-theory of stable infinity categories, which is maybe more intensively studied. But let me maybe start just with a quick reminder on what exact categories are. I don't want to spell out the full definition, but let me remind you that Quillen introduced these as a gadget to speak about algebraic K-theory, and he defined an exact category to be an additive category, call it C, plus choices of certain wide subcategories, which I want to call the inclusions and projections of C, such that certain axioms hold that I don't want to spell out in full. So the way you're supposed to think about these is that every projection arises as the cofiber of an inclusion. Every inclusion arises as the fiber of a projection. And these fiber or cofiber sequences that you get in this way, they are actually bifiber sequences. And they encode a notion of exact sequence in your category. And that's supposed to be enough to be able to speak about algebraic K-theory. The main example that you should keep in mind for the start is that you can always take an abelian category and take as the inclusion the monos in your category and as the projections the epis in your category. And then the notion of exact sequence that you have is just the notion of exact sequence that you're very familiar with. Now, starting from this example, there is an easy observation that allows you to produce many, many more examples of exact categories. Namely, the observation is the following, that if you have an exact category and you have a full subcategory which is closed under extensions, by which I mean when you have an exact sequence in your large ambient category such that the two outer terms of this exact sequence lie in your subcategory U, then the middle term is also in U. So if you have that, then the subcategory automatically inherits an exact structure from C, which you can describe rather explicitly. So the inclusions in your subcategory will be those inclusions between objects in U whose cofiber or co-kernel also lies in U, and similarly for projections. So you know that you can produce new exact categories by looking at extension-closed subcategories of abelian categories. And one of the very basic facts about exact categories is actually that this is the only way how exact categories can arise. And this is, if you want to say this a little more formally, this is the following theorem, which is definitely stated, and a proof is sketched in Quillen's original paper, and he attributes the argument to Gabriel. Then a more detailed account of this appeared in Thomason and Chabot's paper on algebraic K-theory. And then there are other accounts. I'm listing those that I'm aware of by Bühler and by Khaled and Lowen. And I don't want to exclude the option that there are more accounts of this theorem. So what this tells you is that if you have an exact category, then you can do the following. You can look at the category of what I want to call left exact pre-sheaves on C. Maybe just spell this out. Left exact pre-sheaves. By which I mean these are pre-sheaves which are additive, so they preserve the direct sum, and they send exact sequences to fiber sequences of abelian groups. And the statement is that this category is Grothendieck abelian. And you have a natural embedding of C into left exact presheaves, which is just the Yoneda embedding. And this embedding exhibits C as an extension closed subcategory of the category of left exact presheaves. By which I mean not only is the essential image of C closed under extensions in the category of left exact presheaves, but this induced exact structure that it inherits as an extension closed subcategory of this abelian category of left exact presheaves coincides with the original exact structure that you had. So this is sort of the first main structural statement about exact categories that you can make. And well, nowadays, we don't only look at the K-theory of ordinary categories, we also look at the K-theory of infinity categories. And it was Barwick who first suggested that we should maybe look at the K-theory of exact infinity categories. So an exact infinity category is by definition just an additive infinity category with choices of wide subcategories of inclusions and projections, such that the same list of axioms that I did not spell out holds. And if you pass to this greater generality, then one of the additional key examples that you get in addition to abelian categories is that you can look at stable, or a little more generally pre-stable infinity categories, in which you say the inclusions are just all morphisms, and the projections will be those morphisms that arise as cofibers. If your category is stable, that just means you also consider all morphisms. For a pre-stable category, this is slightly more restrictive than you really have to say. You look at those which are cofibers of some map. And this observation that I gave you here, that an extension closed subcategory of an exact category is exact, this is still true if you look at exact infinity categories instead of ordinary exact categories. And well, it's maybe natural to wonder, is there an analog of this statement? And I wouldn't tell you this if there wasn't. So what do you have to do if you want to say something analogous about exact infinity categories? Then it's of course not the correct thing to look at left exact presheaves valued in abelian groups, but instead of abelian groups, you should look at connective spectra. So if you look at the category of left exact presheaves, again, in the meaning these are additive presheaves which send exact sequences to fiber sequences of connective spectra, then you get, well, not a Grothendieck abelian category, but you get a Grothendieck pre-stable category. So this is a presentable and pre-stable category, infinity category, such that filtered colimits preserve finite limits. And now this theorem is just true. Now it's not exactly due to this list of people that are listed here, but this has been worked out by my co-author, Marius Nielsen, and myself. And it tells you, so maybe an additional piece of information that I can give you is that if you have any pre-stable category, you can always embed that into a stable category as an extension closed subcategory. So the upshot of this entire thing is that exact infinity categories, just like ordinary exact categories, are just extension closed subcategories of abelian categories. These exact infinity categories are now precisely the extension closed subcategories of pre-stable or stable infinity categories. So that's one possible description. Something that I would like to mention here already, because I will want to use it later on, even though it's not too relevant at the moment, is the following fact, which was observed by Barwick, that there is yet another slightly different characterization of exact categories, namely exactness is in fact a property. Oops. Of a Waldhausen infinity category. So let me remind you maybe that a Waldhausen infinity category is a category C together with one distinguished class of morphisms, the inclusions or cofibrations or whatever you want to call them, such that certain axioms hold. And Barwick observed that exactness is really just a property of such a structure. And in particular, so this refines a little bit more. So just from the axioms, you know that you have forgetful functor from exact categories to Waldhausen categories. Or I will probably keep dropping the infinity. I apologize now. I will try to say infinity, but I'm not sure whether I will manage. And the statement is actually that this forgetful functor from exact infinity categories to Waldhausen infinity categories, this is fully faithful. So maybe just to introduce a little bit of notation, let me denote by cut x the infinity category of small exact infinity categories. This has a forgetful functor to Waldhausen infinity categories, and this is fully faithful. And maybe note that you can make sense of this category of left exact presheaves that I mentioned here already for a Waldhausen infinity category. And then you could say that for a Waldhausen infinity category, this is an if and only if. So this Waldhausen infinity category is exact if and only if this statement here holds. Now, one nice consequence of this is a statement that was already known beforehand, which I would like to remind you of. So I mentioned that stable categories form a class of exact categories. And in fact, you have a functor from stable infinity categories to exact infinity categories. So let me write cat st for the infinity category of small stable infinity categories. So this has a functor to exact infinity categories where you do precisely what I told you up here, that you take a stable category and you equip it just with the maximal choice of inclusions and projections, namely declaring all maps to be such maps. And then stable infinity categories just become a subcategory of the category of exact categories. And what was already known, this is a theorem due to Clemens, is that this inclusion functor admits a left adjoint. Which I would like to call dB, the bounded derived category of your exact category. So this goes now from exact infinity categories to stable infinity categories. And maybe first of all, I should tell you the following fact to justify my notation. Of course, every exact one category, every ordinary exact category is an exact infinity category. And if you apply this left adjoint to an ordinary exact category, then what this functor does, it actually really takes the bounded derived category of your exact category. So that's my justification for calling this a bounded derived category. So this is really the bounded derived category on ordinary exact categories. Of course, regarded as a stable infinity category. And the relation between these statements is that once you have this, and well, you also have to remember a little bit about the proof of this statement, but then you can deduce from the existence of the Gabriel-Quillen embedding the existence of this left adjoint, because the idea of what you do, so you can sort of write down a formula of what the bounded derived category is in general. Namely, if I have an exact infinity category, then what I can do is I can just look at the pre-stable, the full pre-stable subcategory of this category of left exact presheaves generated by the essential image of the Yoneda embedding. Let me just say generated by C. So this is a certain pre-stable subcategory of left exact presheaves. In particular, this has all finite colimits and it's pointed. So I can take this and take its Spanier-Whitehead stabilization. And this is an explicit model, or more or less explicit model, for the boundary derived category. So this involves, of course, that the way you construct this category here, it comes equipped with a certain universal property that you use to deduce that this actually gives you the left adjoint. So now that we know that we can turn every exact infinity category into a stable infinity category, one question you might ask is, do we have any tools to recognize whether a given stable infinity category is the boundary derived category of something? In that form, there is an obvious and boring answer to this question because well, this is a full embedding, so every stable category is its own bounded derived category, but that's of course a silly answer. That's not the answer I want to give. So the question I want to ask is, can you also recognize more interesting instances of something being the bounded derived category of an exact infinity category? And it turns out that there is something that you can say, which is the following theorem that I proved together with Victor Saunier. Namely that there is a type of structure that allows you to recognize a stable category as the boundary derived category of something. And the structured version of the statement is the following. There is a Gauss field localization where on the one side we just have our infinity category of small exact infinity categories, and on the other side we have something that I still have to define, which I just want to write down. This will be the category of bounded hard categories. I will tell you in a moment what this is. So I claim that there is a Gauss field localization here. And by Gauss field localization, I really mean this is an adjunction and the right adjoint is fully faithful, such that this. So this is almost an equivalence with only a very, very minor failure. The failure is the following, that this localization identifies this category of bounded hard categories as the full subcategory of weakly idempotent complete exact categories. And now the first thing that I should do is tell you what a hard category is. So this is a notion that was introduced by Victor, and which means the following. So let me just give you the definition. If you have a stable infinity category, then a hard structure is a pair of full subcategories such that the following holds. So you require these to satisfy three properties in total. Both of these subcategories are closed under extensions. This positive part of your hard structure is closed under finite colimits. This non-negative part, let me call it the negative part. This is closed under finite limits. So positive part is closed under finite colimits. The negative part is closed under finite limits. And finally, you can decompose every object in some way as a cofiber sequence with something sitting in the negative part and something sitting in the appropriate degree in the positive part. So for every x in C, there's a cofiber sequence with, oops, sorry, x less than or equal to 0 to x greater than or equal to 1, such that x less than or equal to 0 is in C less than or equal to 0 and x greater than or equal to 1 is the suspension of something, oops, I hope you can still read that, of something greater than or equal to 0. So one example that you can think of that you are maybe more familiar with is that if you have a stable category equipped with a weight structure, this is an example of a hard structure. So unfortunately, I've run a little bit out of space here. So when you have such a hard structure, then it has a heart, which is by definition just the intersection of the positive and the negative part. Let me maybe squeeze that in here. So this is what we call by definition the heart. And then there is, just as for T structures or weight structures, there's a notion of boundedness. So we call such a hard structure bounded. If C is the union over all natural numbers, where I take sigma n of C less than or equal to 0 intersect with sigma minus n of sigma greater than or equal to 0. Okay, so this is the notion of a bounded hard structure, and there's an obvious notion of a hard exact functor. This is an exact functor on the underlying stable infinity categories, which preserves both parts of the hard structure and therefore also the hards. And these assemble into this category of categories with a bounded hard structure. And then the way you extract from a bounded hard category an exact category is by taking its hard. And in the other direction, there is an obvious candidate of what you want to do. You take the bounded derived category and, well, it's not enough to specify the bounded derived category. What you do is you take the bounded derived category in this sense here. And now I'm claiming that this carries, always carries a bounded hard structure, which sort of canonically comes from this construction that you're doing here. So basically, since you define this as the Spanier-Whitehead stabilization of something, this something is what will be the positive part. And then, well, you also have to define the negative part. Maybe let me not go too much into details here. Also, so I can advance to maybe the more interesting statements that are supposed to come later on. As a final remark, let me mention that since I already mentioned weight structures, that this localization that I've stated here, this restricts to a Bouwspeed localization between additive infinity categories. These also form a full subcategory of this infinity category of small exact infinity categories, precisely as those exact categories equipped with a split exact structure. So where the inclusions are just the inclusions of direct summons and the projections are just the projections onto direct summons. And these become identified up to weak idempotent completion with the categories carrying a bounded weight structure. And this is a statement that was known already before. This is due to Sosnila, who proved this version. So the theorem that I gave you here is a generalization of Sosnilo's theorem, which tells you not only what to do with split exact categories, but with arbitrary exact infinity categories. So these are some comments on how stable infinity categories and exact infinity categories relate to each other on the categorical level. But what I want to talk about now in the remaining 35 minutes is actually what can we say about the algebraic K-theory of these things. So let's move on unless there are questions to algebraic K-theory. I think that many of us like to think about algebraic K-theory nowadays as a functor on stable infinity categories, which is mainly due to the work of Blumberg, Ebner, Tabuada, who have shown that if we consider algebraic K-theory as such a functor, that it has a very nice universal property that allows us to sort of conceptually understand what algebraic K-theory is actually supposed to be. But let me also mention, if you like to widen your context, not only speak about stable infinity categories, but about Waldhausen infinity categories, that Barwick has also proven an analogous universal property. So the universal property is that if we want to talk about connective algebraic K-theory, that this is the universal group-like additive invariant under the groupoid core. And there's more you can say. You can also give an explicit construction of what this is, namely connective algebraic K-theory can be explicitly described by the Siegel-Waldhausen construction. So in the following, I want to think about connective algebraic K-theory as a functor valued in connective spectra. So let me maybe for the formula now tell you what the infinite loop space of K-theory is. This is given by the following, or let me also evaluate this on a category. So depending on which framework you prefer, C is now either a stable infinity category or a Waldhausen infinity category. Then one way to describe this is you take your category, you apply the S dot construction to this, you take the groupoid core of this thing to obtain a simplicial space, you realize the simplicial space and then take its loop space. And that's sort of the classical description, at least more. Well, it's one of the classical descriptions, let's say like that, of algebraic K-theory, the one that that Waldhausen introduced. So you might say there's now a little tension in what I've been saying. So if I have now an exact infinity category, there's more than one thing that I can do. I can either just take this exact infinity category as a Waldhausen infinity category and take its algebraic K-theory. That's something I could do just to define what its algebraic K-theory is. I could also say, well, I always prefer to think about stable infinity categories, so I just take my stable infinity category. I know that there is this left adjoint, so I take first its bound-derived category and then look at the K-theory of that. And the first reassuring thing is that these are actually the same functors that you're describing. So let me call this the Gillet-Waldhausen theorem, just for the reason that this is the name of this statement if you look at ordinary exact categories. So for ordinary exact categories, this is due to Thomason. If you have an exact category, then C includes into the bounded derived category of C. And after applying K-theory, this is an equivalence. And this just generalizes to exact infinity categories. So this is also something show together with Victor, that if you have an exact infinity category, there's still a comparison map. This is the unit transformation of this adjunction between exact categories and stable categories that I told you before. That gives you an exact functor from C to its bounded derived category. And after applying K-theory, this is an equivalence. So we at least have an unambiguous way of talking about the algebraic K-theory of an exact infinity category. Now, one of the key features of algebraic K-theory is that, well, if you want to describe its universal property, it's enough to talk about additive invariance, but actually algebraic K-theory is much, much better behaved. So something that one of the great things I think about algebraic K-theory is that it is localizing. So let me not try to give you a precise definition of what this is supposed to mean, but let me only give you an approximate definition of this. So when I say it's localizing, I want to say there are certain co-fiber sequences of input categories that give rise to fiber sequences in algebraic K-theory. Induce fiber sequences in algebraic K-theory. And of course, the interesting ones, which are not just encoded in the notion of an additive invariant, are co-fiber sequences which are not split. And when I give you this this vague statement now, then I'm doing this with the intention that maybe depending on who I would ask, you would give me different localization theorems that you come up with when I ask you about localization algebraic K-theory. So the ones I can mention spontaneously are there's a localization theorem for stable infinity categories. On the ordinary side of things, there's Quillen's localization theorem for abelian categories. And then Marco Schlichting also has a localization theorem for exact categories. But somehow, I mean, these are close together somehow in the type of statement that they give you, because they all are of this flavor, and they tell you that certain co-fiber sequences induce fiber sequences. But to my knowledge, it's not been entirely clear of what the precise relation between these statements is. And that's what I want to talk about next, because instead of talking about those theorems, I first want to give you a different localization theorem that I hope you haven't seen before, which is the following. Suppose you have an exact infinity category, and suppose you have an extension closed subcategory, and let me assume, just for simplicity, that this subcategory is idempotent complete. So there is a version of the statement that I'm about to give you which does not require this, but makes the statement slightly more technical, and I don't think it really helps to digest what I'm about to say. So let's just assume that U is idempotent complete. And then I want to impose one additional, what I would like to do, let's say it like that, is I would like to impose one additional condition. Unfortunately, this will not be quite enough, but for the beginning, let me give you the condition that I want you to think about, and then I will be more honest. I would like you to just think about the situation that this inclusion is filtering. And of course, I have to tell you what I mean by that. So let me first give you the definition of filtering. Filtering is supposed to mean the following. Let me maybe put this down here. So in the situation that I have an exact infinity category and an extension closed subcategory in there, then I call U in C filtering if and only if the following holds. Suppose that you have any object in U, an arbitrary object in C, let's say some natural number K, and you look at an arbitrary element now in pi k of the Hom from U to X. So think about that as we're looking at arbitrary finite families of morphisms from an object in U to an object in X. Then I require the following. Then I ask that there exists a projection in C with the property that the fiber of this projection is an object in U. And when I take my given finite family of morphisms and just map them further to x prime, then this becomes 0. So any finite family of morphisms from an object in U to an object in C becomes trivial after mapping a little bit further. So after post-composing with a projection whose fiber is in my subcategory. And now, morally, what this theorem is supposed to say is that if you have such a filtering subcategory, then the resulting sequence K of U to K of C to K of the cofiber is also, in this case, even a cofiber sequence of connective spectra. Now, so far I've only said that I want to put some cofiber here. So here's a little subtlety in the statement. The statement that I can actually prove is that I don't want to put here the cofiber among exact infinity categories, but what I actually want to put here is the cofiber of this inclusion among Waldhausen infinity categories. So remember that I told you that exact infinity categories sit as a full subcategory in Waldhausen infinity categories, but I'm claiming this inclusion does not preserve cofibers in general. And for this statement, it's actually important that we take the cofiber in Waldhausen infinity categories, not in exact infinity categories. And you will see in one instance of this phenomenon in a moment. So this is basically the statement that I want you to think about. As written, this is not quite correct, but you have to impose slightly stronger assumptions. Namely, what you actually have to impose is the condition that SNU in SNC is filtering for all n. Now, this looks maybe not too promising because instead of this one inclusion, I'm now suddenly looking at all these inclusions of these categories that appear in the S dot construction. But this condition is not as bad as it looks on first sight, because I want to claim that this is equivalent just to two conditions, requiring that U in C is filtering, and one further condition, which looks maybe a little bit odd, and I'm not expecting you to memorize it right away, but I want to write it down once just so you see that it's a condition that's fairly explicit and just happens, or it's just really a condition on this inclusion of U into C and nothing else. So the condition is the following. Whenever you have, let me write this type of arrow for an inclusion in C, and you have another map, let's say y to y bar, and this is a projection in C, and let me maybe indicate this by a twiddle with a U subscript. This is a projection with fiber in U, so this is supposed to be my notation now for saying this morphism is a projection in C with fiber in U. So whenever I have two morphisms like this, then I can complete this to a diagram of the following form. So let me repeat the data that I have. Then what you need to find, let me make a little bit more space here. Then you must be able to find a morphism from y bar to some y prime with the property that this composite that you get here is still a projection with fiber in U. And you have to be able to find a projection with fiber in U from x to some x prime and an inclusion from x prime to y prime such that this here can be filled, so that you find a commutative square like this with all the arrows of the type as I've tried to indicate. So once you know this, I claim so these two conditions are equivalent to requiring that all these inclusions are filtering. And as I said, the reason why I write this down is I want to show you here these are really conditions that only speak about the inclusion of U into C. You don't really have to look at the S dot construction to verify the assumption. Okay, so this looks maybe a little bit wild, but I want to claim that this is actually a generalization of of the three theorems that I mentioned before. And I want to try and use my remaining time to convince you, or to at least sketch why this is the case. So let me maybe introduce a little bit of language. Let me call this condition here that U in C is strongly filtering. Just to make this a little bit shorter. And let me now repeat the statement of this theorem once more. So if I have U in C strongly filtering, and idempotent complete is what I wanted to say. Then K of U to K of C to K of the Waldhausen cofiber of this inclusion is a cofiber sequence of connective spectra. So this is just the theorem that I just gave you. And now let's start thinking about the other theorems that I mentioned. So let's look at the localization theorem for stable categories. What does this say? It tells you that if C is a stable category and U is a full stable subcategory, and again, just for simplicity, let's also say U is idempotent complete. Then K of U to K of C to K of C mod U is a cofiber sequence. Where by C mod U, I now mean the Verdier quotient of these stable categories. But without any sort of idempotent completion. It's really just the cofiber in stable infinity categories. So how do these statements relate to each other? Well, the claim now, of course, is that if I have a full stable subcategory, it's supposed to be strongly filtering. And well, since the S dot construction applied to something stable still is something stable, it's enough to show that a full stable subcategory is filtering. So how do you see that? What we have to do is, if we look at pi k of hom u x, we want to show that any element we pick in here can be trivialized by post-composing with a morphism whose fiber is in U. So how do we do that? Well, since everything is stable, we can shift things into degree 0 if we like. So I can also think about this as pi naught of maps from U to loops k of x. And if I now imagine that I have an element here, then there's an obvious way how I can trivialize that. I can just map further to the cofiber of f. So I can map here to pi naught hom u cofiber f. This has the effect that f becomes null homotopic. And of course, I can shift this back. I get here pi k hom u sigma k of the cofiber of f. And this is the proof that a full stable category, subcategory, is filtering. So this theorem up here applies in this situation to tell me that I have this cofiber sequence here. Now there's an additional piece of information that I've swept under the rug so far, namely there is actually a fairly concrete way of thinking about this Waldhausen cofiber under the assumptions that I gave you. So this is an additional piece of information that I should now provide. In the situation up here, we know more. We know that we can describe this Waldhausen cofiber of the inclusion of U into C as just a Dwyer-Kahn localization of the category C. Namely, what we do is we take C and we localize. Let me maybe use a shorthand for this. Let me write these symbols for the projections in C whose fiber lies in U. And we're just localizing at these arrows in C. If you now think about the case of a stable infinity category, what is this localization? This means I take C and I localize C at all morphisms whose fiber lies in U. And well, this is a description of the Verdier quotient. So this Waldhausen cofiber that appears in this theorem in the case of stable categories is just the Verdier quotient that you get. So what this is supposed to tell you is that the theorem I gave you implies the localization theorem for stable infinity categories. Now, in the next step, I want to explain to you why another theorem follows, which you maybe not necessarily consider to be a localization theorem, but it nevertheless fits nicely into the story. Namely, the next theorem that I claim follows from the theorem on the top is Barwick's theorem of the heart. So the statement here is that if you have a stable infinity category with a bounded T structure, then you can look at the inclusion of the heart of C into C itself. And after applying K-theory, this is an equivalence. I should emphasize connective K-theory. All the K-theory that I've been looking at has been connective so far. So why is this a consequence of the theorem that I gave you up there? So here's a sketch of how you prove the theorem of the heart. In the first step, you observe that if you look just at the positive part of the T structure, if your T structure is bounded below, then you can recover C from the positive part just as the Spanier-Whitehead stabilization. So the Spanier-Whitehead stabilization, maybe recall one description of this is that you look at the suspension functor on this category and you just iterate the suspension functor over and over, and you take the sequential co-limit along iterations of the suspension functor, and that gives you the Spanier-Whitehead stabilization. And so since suspension induces an equivalence on K-theory, taking the Spanier-Whitehead stabilization of something doesn't change the K-theory. So since we have this, this tells us already that the inclusion of the positive part of the T structure into C is an equivalence if the T structure is bounded below. In the second step, you can look at the inclusion of the heart into C. And what I maybe only want to claim now is that this is in fact strongly filtering. So that it's filtering basically follows from the fact that you have the T structure. Because if you map something in the heart, or sorry, I should say here in the co-connective part. So if you map something in the heart to something co-connective, then you can just map further to the -1 truncation of this object, and then the composite will become trivial. That's the basic reason why this is filtering. So this is filtering, and moreover, we can identify this Waldhausen cofiber in this case. Namely, what this Waldhausen cofiber is, it's the full subcategory of -1 truncated objects, but not equipped with its canonical exact structure. But what you get here is, let me denote this, max. It's the Waldhausen infinity category structure in which every morphism is an inclusion or a cofibration, if you like. And in particular, this is not an exact structure. So this is really just a Waldhausen category. And now the point is that if your T structure is bounded below, then the Spanier-Whitehead stabilization of this thing is trivial. So if you have a T structure which is bounded below, this tells you now, applying the theorem up here, that the inclusion of the heart into the co-connective part is also an equivalence. So what we know, if the T structure is bounded below, then the inclusion of the positive part into C is an equivalence in K-theory, and the inclusion of the heart into the co-connective part is an inclusion in connective K-theory. And then you have to play around a little bit more with the fact that K-theory is invariant under taking opposites. And if you invest that in addition, then this is a bit fiddly. I don't want to try to spell this out now, but then you combine the two statements that I explained to you to see that actually the inclusion of the heart into C is an equivalence. So this is supposed to convince you that the theorem upstairs also implies the theorem of the heart. And now that we have that, we're only a very short way away from proving Quillen's localization theorem. So let's recall what this says. This says if I have an abelian category and a Serre subcategory in there, whoops, then I get a cofiber sequence K of U, K of A to K of A mod U. Well, let me maybe not write this down. By A mod U, I now mean the quotient in abelian categories. So this is the abelian quotient category. That's why I'm writing A mod U. And how can we deduce this from what we already have here? Well, what you can observe is that this abelian quotient category also has a fairly explicit description as the localization at the class of isomorphisms modulo U. And playing around with that, you can see that if you pass to boundary derived categories, that the induced functor from dBA to dBA mod U, this is a Verdier projection. And consequently, you can always look at the fiber of this thing to get a Verdier sequence. And so this notation down here, this is now the full subcategory of the boundary derived category of A on those complexes whose homology lies in U. This is precisely the kernel of this functor here. And now, well, if I'm looking here at all the complexes whose homology lies in U, then I can observe, apologies, that the canonical T structure that I have on the boundary derived category of A, that just restricts to a T structure on the boundary derived category of this, on this stable infinity category here. And what's the heart of this T structure? It's just U. So applying the localization theorem for stable categories to this Verdier sequence and using the theorem of the heart for this kernel, you see that you get. Okay, you have to apply, sorry. You have to apply the theorem of the heart to all three terms, of course. And then you see that you get precisely this cofiber sequence. So if you combine the localization theorem for stable infinity categories and the theorem of the heart, then you get this. So I'm not quite sure how well documented this argument is, but for example, there's been a recent preprint by Efimov about the Devisage theorem, where he basically also does this argument how Quillen localization follows from the theorem of the heart. Okay, and I promised you one more localization theorem, namely Schlichting's. So let's talk about that as well. And that says the following. Suppose now that C is an exact one category. Just putting this there for emphasis. And you have U in C, a category which is extension closed. Filtering idempotent complete. And has one additional property, which I for short just want to call special. And I will explain, hopefully in a moment, what special means. Then you also get a cofiber sequence K of U to K of C to Okay, and now here you can actually put the exact cofiber of U into C. The thing is, there are now actually two arguments how you can derive this theorem from the others, and this was also already observed by Schlichting himself. So let me give you one of the two options that you have. What you can do, for example, is you can say this requires a little additional argument that I want to skip, but here I'm now really looking at a cofiber sequence in exact categories. And I have this left adjoint functor from exact categories to stable categories. So I want to claim upon taking boundary derived categories, I get a cofiber sequence of stable infinity categories. The small detail that I'm skipping here is that the question, what type of category is this? And the special thing which happens because the inclusion is filtering is that the quotient exact one category is also the quotient exact infinity category. That's something you need to argue why this is the case, but it's true, and so we don't have to worry about that distinction. So what we get here is that dBu to dBc to dB of this cofiber, this is again a cofiber sequence. So what I claim is what we've used so far is that U in C is filtering, and that's it. So the question is, what does special buy me? And special will buy me that this here is actually a Verdier sequence. And that has the following reason, which is maybe the last thing that I should tell you, so I don't go over time. So let me first tell you what special means. If I have an extension closed subcategory, then U in C is special if the following holds. Whenever I have a projection from an object in C to an object in U, then there exists another object in U and a morphism from this object V to X, such that if I now compose the two morphisms that I have from V to X and from X to U, such that V to U, that this is a projection in U, meaning it's a projection in C whose fiber also lies in U. So that's what it means to be special. And then the proposition is the following. So for exact one categories, this is originally due to Keller. And then, well, we've given two separate arguments, one in my paper with Marius and one in my paper with Victor. If you have a special inclusion, then the induced functor on boundary derived categories is still fully faithful. If you believe this, then now we don't only have a cofiber sequence here, but this here is actually a fully faithful functor. So we have a Verdier sequence here, and therefore we can apply the localization theorem for stable categories to see that we also get this cofiber sequence in connective algebraic K-theory. So maybe if I shift this a little bit upwards, so now you have this little flow diagram here. So starting from the theorem above that I told you about, all these other statements follow as consequences of this thing. Unfortunately, I don't have any exciting new application of this theorem to tell you about. It's only that I can say this theorem unifies the localization theorems that we've known about for some time already, for a while. And that's all I want to tell you. Thank you very much.
Thank you, Christoph. Let's give the speaker a round of applause. Do you have any questions for the speaker?
Oh, yeah.
Yeah, and go.
How much can you say about non-connective K-theory? What carries over or what's open?
Yes. So the theorem that I gave you here, this cannot have an analog in non-connective K-theory, because if it did, you would be able to run this argument to see that the non-connective theorem of the heart is always true, and we know this fails. So this statement up here that I gave you, this is somehow genuinely a statement about connective algebraic K-theory. Of course, we know that the localization theorem for stable infinity categories carries over to non-connective K-theory. For Quillen localization, maybe what's already clear from the way I've presented this is that the version I gave you here, I do not know whether it holds for non-connective K-theory. If you're willing to replace this here by the K-theory of this full stable subcategory, then it also holds non-connectively, because it's just an instance of the localization theorem for stable categories. And somehow what you can also show is that if you look at inclusions of special subcategories, these always give you fiber sequences in non-connective K-theory. That's basically a combination of the fact that they induce co-fiber sequences, or they induce Vertier sequences on their stabilizations, and that the Gillet-Waldhausen theorem also holds non-connectively. That's one way to think about it.
Yeah.
Okay, Marco. Any other questions?
Maybe one additional thing, sorry, but what I should say, if you look at special inclusions, it's also true that the Waldhausen co-fiber always coincides with the exact co-fiber. So for special inclusions, these are really the same co-fibers that you get. So this distinction goes away for special inclusions.
So you don't expect your theorem to be, or maybe you do expect, I don't know, to be true for, like, except for algebraic K theory. What other kinds of additive invariants or localizing invariants could you envisage that this theorem could hold?
The proof there that I give this very much uses the S-dot construction. So I do not know how to generalize this to other additive invariants. Yeah, I think this is all I can say. The proof for this statement, this is completely in terms of the S-dot construction. I see no way around that at the moment.
Yeah. Okay. Thank you. Any other questions? If we don't have any more questions, let's thank Christoph once again.
Thank you.
Would you be fine with sharing the slides with me afterwards?
Yeah, sure, I can do that.
Thank you. Thank you again.